So in this section we're going to look at the calculus of parametric curves. So suppose we're given a parametric curve described by the parametric equations x equals f of t, y equals g of t, and let's suppose f and g are differentiable and y is also a differentiable function of x. Then the three derivatives dy dx, dy dt, and dx dt are related. Using the chain rule, we find dy dt is dy dx times dx dt. Using this, we can obtain a formula to compute dy dx from dx dt and dy dt. If we divide across by dx dt, we get dy dx is dy dt over dx dt. Now, we're not assuming here that y is some function of x for all x. We can apply this formula locally at a particular point as long as y is a function of x near the point. The value of dy dx gives us the slope of a tangent to the curve at some given point on the parametric curve C. So this helps us draw the graph of the curve and get some idea of how it's changing. The curve's going to have a horizontal tangent when dy dx equals 0 and a vertical tangent on the xy plane when dy dx equals infinity. And now we can actually calculate the second derivative, and the easiest way to calculate this is to note that the second derivative of y with respect to x is the derivative of the first derivative with respect to x. And of course that's the derivative of that function with respect to t divided by dx dt, assuming again that dx dt is non-zero. Well, let's use this. Suppose I want to find an equation of the tangent to the curve x equals t squared minus 2t, y equals t cubed minus 3t when t is minus 2. Now I don't have to draw this curve. I can use the formula for dy dx. We need two things for the tangent. We need a point on the curve and the slope of the tangent, which is dy dx. So when t is 2, the corresponding point on the curve is the point P with x value 4 plus 4, that's t squared minus 2t, and y value minus 8 plus 6, and that's t cubed minus 3t. So when t is minus 2, the corresponding point on the curve is at x equals 8, y equals minus 2. Well, now we want the slope of the tangent through that point, so we must calculate dy dx, and of course this is dy dt divided by dx dt. So dy dt is 3t squared minus 3, and the derivative of x with respect to t is 2t minus 2. Whatever the t value is, dy dx is 3t squared minus 3 over 2t minus 2 by our formula, and this gives us the slope of the tangent as long as 2t minus 2 is non-zero. Well, when t is minus 2 at our point of interest, we see dy dx is minus 3 over 2. So we have a tangent that's sloping downwards. And the actual equation of that tangent line at that point is y minus minus 2 equals minus 3 over 2 x minus 8. So y plus 2 equals minus 3 over 2 x minus 8. And here we see a picture. When t is minus 2, the corresponding point on the graph is here, and we have the slope of this tangent line running through that point is minus 3 over 2. So it's sloping downwards, and its equation is y plus 2 equals minus 3 over 2 x minus 8. Well, suppose I want to find the point on the parametric curve where the tangent is horizontal. And we can actually see this from the graph here. This is going to be right here at this point. We're going to have a horizontal tangent. So we would like the value of t at that point and the x coordinate and y coordinate. we can solve for these if we set dy dx equals 0, and dy dx is 3t squared minus 3 over 2t minus 2 by the equation. That's dy dt over dx dt. Dy dx equals 0 if this quotient is 0, and of course this happens if 3t squared minus 3 is 0 and the denominator is non-zero. If 3t squared minus 3 is 0, then t must be equal to plus or minus 1. When t equals minus 1, then 2t minus 2 is non-zero, so certainly dy dx is 0, and the graph has a horizontal tangent at that point. And the corresponding point on the curve is x equals t squared minus 2t, which is 3, and y equals t cubed minus 3t, which is 2. When t equals 1 here, we have dx dt is 0, and also dy dt is 0. So if this curve is describing the motion of a particle, then at this point the particle has stopped because the change in x with respect to time is 0 and the change in y with respect to time is 0. And if we look on the graph of the curve, when we plug in t equals 1, we get the point minus 1 minus 2, and we see that the curve has a cusp at this point, or a very sharp point. Locally, the curve cannot be described in terms of y equals a function of x because it doesn't pass the vertical line test. The curve is not a differentiable function of x at this point, so it doesn't make sense to talk about a tangent to the curve at this point. Let's see what we can say about a vertical tangent. Does the parametric curve have a vertical tangent? So now we're looking for a point where dy dx is equal to plus or minus infinity. So we want 3t squared minus 3 over 2t minus 2 to equal plus or minus infinity, and this will happen if the denominator is 0 and the numerator is non-zero. Now dx dt here is 2t minus 2, so that's 0 only if t equals 1. However, in that case, dy dt equals 3t squared minus 3, which equals 0, and our curve doesn't have a vertical tangent. Well, let's calculate the second derivative to figure out where the graph is concave up and concave down. The second derivative of y with respect to x here is the derivative with respect to x of dy dx. That is the derivative with respect to t of dy dx divided by dx dt by our formula from the chain rule, as long as dx dt is non-zero. So if dx dt is not equal to 0, we have dy dx equals 3t squared minus 3 over 2t minus 2. This is equal to 3 over 2 t plus 1 after we cancel out the t minus 1 in the denominator. So the derivative with respect to t of 3 over 2 times t plus 1 divided by dx dt, which is 2t minus 2, is 3 over 4 t minus 1. And we see that this is greater than 0 if t is bigger than 1, and it's less than 0 if t is less than 1. So this means our graph is concave up if t is greater than 1, and concave down if t is less than 1. And remember, on our graph, the point where t equals 1 is the point at the cusp, so we see that the graph is concave down for t less than 1, and we see our graph is concave up for t greater than 1.